You've got some kind of mass. You step on a scale. Great. You've got your mass. Except that you don't. When physicists like me came up with the idea of mass, they did not know they were about to create one of the greatest misunderstandings between society and physics. But what did they mean by mass? How do you get it? And what is a scale actually showing? Let's measure your mass. But let's do it the scientific way. The mass of something depends on its size and density. In other words, on the amount of stuff it's made of and the kind of stuff it's made of. Mass is a fixed property. A 1 kilogram or 1 pound weight will always weigh 1 kilogram or 1 pound, no matter where you take it. In principle, your mass is also fixed, but you're constantly adding or losing things from your body. Your volume and density change. So does your mass. But in principle, in this very moment, your mass is fixed, no matter if I weigh you here on Earth or teleport you into space. So, step on this scale. It'll tell you that you weigh nothing. On Earth, this was a bit more. Let's test the weight. It also gives 0. This happens because the scale measures something different from mass. It measures the strength of our connection to the ground, how tightly we're bound to the Earth. It measures how strongly gravity pulls on us. We call this weight, just like the weight. Gravity happens because all things attract one another due to their masses. All things, no matter what. But if masses are small, their attraction is barely noticeable. So most of the time, we're talking about Earth's gravity if we mention gravitation. Therefore, your weight depends not only on your mass, but also on the masses around you. Just like this channel depends on your support. So please subscribe and like if you'd like to. Weight and mass are not the same. That's just a great misunderstanding between society and physics. Since your weight is about your mass and the masses nearby, the very heavy masses, on the planet's mass that pulls on you. In space, there's no planet close by, no gravity. You basically weigh nothing. On Earth, the scale shows you different weights depending on your location, because gravity's pull depends on the distance between you and Earth's center, since gravity originates there. So, your weight, mainly shaped by gravity, varies depending on your location. If you're standing at the top of a mountain, less gravity acts on you. You are light. Closer to the center of Earth, your weight increases. So, if we want to measure your mass, we do it not like this. We know scales do not measure mass. Okay, but how do we figure out mass? We do it like this. Actually, scales measure gravity's pull and then try to calculate your mass out of it. Being very close or far away from Earth's center, this fails. But almost everywhere on Earth, the scale reads your weight as the same. Here, mass and weight match. The scale calculated your mass correctly. First, it measured gravity's pull, which is 687 Newton in the case of a person. We'll see how to calculate your mass from that. To get there, we have to look at this pull from gravity. This pull makes things fall down. Those things speed up while falling. This speeding up is called gravitational acceleration. It is a number, the same number for everything on Earth. Since gravity causes it, we already know what it's based on: Earth's mass and the distance to Earth's center. So, the gravitational acceleration is a number telling us how fast things speed up while falling to the ground. It's smaller being far away from Earth and bigger closer to Earth's core. But in most places on Earth, it's 9.8 meters per second squared. This number is easy to find by measuring the time and distance something falls. Knowing this number and measuring gravity's pull, the scale can calculate your mass. Great. But this does not work if you're not on Earth. Gravitational acceleration is only this fixed number on Earth. It depends on Earth's mass and radius. On Moon, it's influenced by Moon's mass instead. In space, it's 0. That's why the scale can't calculate your mass correctly if you're not on Earth. It assumes Earth's mass and therefore Earth's gravitational acceleration. Okay, So a scale tries to show mass, but it shows weight. How much you weigh depends on your mass. The bigger your mass, the stronger Earth's gravity pulls on you, the bigger your weight. The scale tries to calculate your mass from that. For the most part, this works just fine on Earth. That's why, in everyday life, weight and mass are mostly the same. And why we measure mass like this, even though scales do not directly measure mass. Great, measuring your mass was a bit more complicated than expected. At least the implementation is easy. Just step on a scale anywhere on Earth, not too far above or below Earth's surface. You get your mass. But if we are only able to measure masses while standing on Earth's ground, how can we ever figure out Earth's own mass? We'll discover this in the next video next week. In the meantime, take a look at the video where we dive into Newton's underlying theory. Thanks for watching. Please drop your questions in the comments and subscribe to find out how it actually works.